Dear viewers, today our discussion is about R2R laddered network. It is the initial stage of a DAC, so we can call it as a digital to analog converter. Now, what would be the objective of today's discussion? We'll first have a very brief idea about D2A converters. Then we will see the construction of a 4-bit R2R ladder network. Then we'll have analyze the 4-bit R2R ladder network, and we will sum up the entire session with the help of a simple numerical example. Now, what is a DAC? Now, DAC is we call it digital to analog converter. It's commonly used to convert digital data streams into analog signals. Now, they are very much in use in televisions, mobile phones, audio systems, and data communication equipments to convert the digital audio video data into the corresponding analog audio video signals. There are two types, there are two applications use DAC at opposite end of frequency and resolution trade-offs. Well, when we are talking about digital to analog converter, R2R ladder network is one of the type, and in this circuit configuration, commonly it is used to convert digital signal into analog voltage. Its corresponding analog voltage. Well, it consists of a network arrangement produced or constructed out of resistors arranged in a specific ladder pattern to create different voltage levels corresponding to binary inputs. Well, the name 2R, R2R, where R is the reference resistor and reference resistor in the ladder network, and 2R is twice the reference resistor. So let's have a look at the construction of R2R ladder network. Ladder networks are usually constructed in this fashion. You can see these are the digital inputs to the power 0, 1, 2, and 3. These are the digital inputs where right hand side is the most significant bit and the left hand side here is the least significant bit. And we have a ladder network consisting of R and 2R network, and this is the output voltage, which is VA. So again we can see that the digital inputs are hereby denoted by 2 to the power 0, which is 1, 2 to the power 1 is 2, 2 to the power 2 is 4, 2 to the power 3 is 8. So this has been designed in the increasing weight. So these are the digital inputs. Here you will have either a zero logic or a high logic. That means either you will connect this particular terminal to a low or to a high. Now it all depends. The high can be plus 5 volt, high can be more than that. So the output voltage VA will be the corresponding proportional output voltage corresponding to the digital combinations that has been given at the input of this. Okay, so to let us start analyzing the circuit. In order to analyze the R2R ladder network, what we have to do is, first of all, what we will do is we will connect the 2 to the power 0 input, that is the least significant bit, to ground. So we are considering a situation where we will one by one connect all the inputs to the ground and check what happens to the circuit. Now when we connect the output, that is extremely sorry, when we connect the input, that is the 2 to the power 0 input, to the ground, this particular section, which is just around A, on the left side of A, these two resistive network are now in parallel. So when they are in parallel, what we will get is the equivalent resistance from this particular network, and we know R equivalent. If we consider that to be R equivalent, here this means R, two R's, actually two R are parallel. Both the resistances are in parallel, and we'll consider the equivalent resistance of this particular network, and that will be 1 by 2R plus 1 by 2R, which is 1 by R. So R equivalent is actually R. So we will replace the circuit on the left side of A with a simple R. Here you can see the portion left to A has been replaced with a simple R. Now the same thing will happen when we connect the circuit next to left to B. Here also you can see we have 2R and we have 2R, and when we connect 2 to the power 1 to ground, this particular section is in parallel, and hence again this can be replaced with a equivalent value of R. So again, if we check the other section where we will be now connecting 2 to the power 2 to the ground, again to the left of C. Here we have 2R, here we have 2. Again it is in parallel combination, and again it will be replaced by a R to the left of C. So now since we have seen a technique of analyzing this particular R2R ladder network, now let us assume that we have provided a digital input to the D2A converter, where the most significant bit, that is 2 to the power 3, has been connected to say plus volt V. Then the output voltage, what we will compute VA, would be, that is for 1000. 100 here is the digital input, and we'll be computing the output voltage VA with respect to the digital input voltage V. So let's see the circuit. Here we can see that we are applying a digital input to 1000. Here 100, here 1 is applied at the most significant bit and followed by other bits. Here the most significant bit position is here, so this is connected with plus V, and others are grounded. Now if we look into this particular circuit, we have already seen that if we connect this to the ground, then this is equivalent to R, which is again equivalent to 2R. When they both are in parallel, again this section becomes R. So this particular section which has been circled can be again written in this manner. So what we have got a simplified circuit where we have a VA, we have one of the resistor connected to the ground, another resistor connected directly to the logic input, which is the voltage is V. So now we can find out the output voltage VA by just applying the potential divider formula, where it says that the voltage that has to be measured across any resistance, then that particular resistance divided by the total resistance into the applied voltage. So here the total resistance is 4A. From this we can see the total resistance is 4R. Here it is the 4R. So at the bottom we have the total resistance, and above we have the resistance across which we will be getting the voltage, that is VA. So this resistive network will be multiplied with the total voltage, that is the voltage applied as V. From this particular expression we can see the VA is nothing but V by 2. So in the similar fashion we will be considering other inputs. Now we will consider a situation where we have applied a digital input which is 0100, where other three inputs are connected to ground except the second bit after the most significant bit, which is this position. Now we will see how we can analyze this particular circuit. Now, when we analyze this particular circuit, it's usual that on the left hand side under the circle, we can see this particular circuit will be replaced by 2R. This particular section will be replaced by an R with another R, and on the left side of the C, we can see it is 2R. So now the circuit is bit complex to the earlier circuit that we have analyzed. In this circuit, we have to calculate the output voltage here, and we have a complex circuit which includes V and several resistors. So in order to get the output VA, what we do is we will apply Thevenin's theorem into this particular circuit. Now let's see how to apply Thevenin's theorem into this particular circuit. First of all, the portion which is inside the circle will be severed from the right side, and since this part is the load part and this part is the source part, what we'll do is we will sever this section and try to analyze the circuit under this. So the left side of this, that is the circuit inside the circle, can be replaced by an equivalent circuit which will consist just of Thevenin's equivalent voltage source in series with a Thevenin's equivalent resistance. So what we will do is we will try to sever this, and once we sever this, the right hand side will not be there, and we will now try to analyze this particular circuit. Now once we do the analysis, as this is again the simple network comprising of a resistive network, we will assume we will first assume that we are going to measure the Thevenin's equivalent resistance. So in order to measure the Thevenin's equivalent resistance, the first thing that we will do is we'll have to remove all the source from the circuit, replace it with its equivalent resistance. Now we know that the internal resistance of any voltage source is almost zero. So what we will do is we will replace it with a short circuit and connect it to the ground. Now again we can see that the circuit given here is a parallel combination these two resistive networks. So these two resistive networks will provide us the equivalent resistance looking into the circuit, equivalent to Thevenin's resistance, which is denoted by RTH. So it is again the parallel combination of 2R and 2R. When we compute the equivalent resistance, we'll get the value R. So we have got the Thevenin's equivalent resistance. Now to compute the Thevenin's equivalent voltage source, what we'll have to do is we'll have to again consider that particular circuit and consider the voltage just across C. We will try to measure this particular voltage. Now in a practical circuit we can measure it, but in theoretically we'll have to compute the value of VC here. So in order to do that, what we will do is we will again, you can just have a look at the circuit. It is again a potential divider circuit. So we will again apply the potential divider formula since we are measuring the voltage across this R. So this resistance divided by the entire resistance multiplied by the voltage applied. So what we have is 2R divided by 4R into plus V. What we'll get is V by 2. So the Thevenin's equivalent voltage source, which has been denoted here as VC, is V by 2. Now what we'll do is we will now draw the Thevenin's equivalent circuit, which consists of the source which we have already computed as V by 2 in series with resistance R. This is the Thevenin's equivalent resistance we have already seen in the previous slides, and we will now attach the load part of the circuit with this particular circuit. Now what we will do is we will now try to compute VA. So how can we compute that? Now we see, what we can see here is the Thevenin's equivalent voltage source, and this R is the Thevenin's equivalent resistance. Now in this particular circuit, if we want to calculate VA, what we can closely observe is, again, we are trying to calculate the voltage across D, which is across this particular resistance, that is 2B, and here again the two resistances are in series, which is again 2R. I'm extremely sorry, the voltage across D is again, the voltage will be calculated across this resistance, which is 2R, and again we can see on the left side of D we have two resistance, each value R are in series, so again this will be 2R, and this is connected to a voltage V by 2. So again, if we want to measure VA, we again have to apply the potential divider formula. Since we are measuring VA across this resistor, so 2R divided by the total resistance, which is 2R plus 2R, into the voltage V by 2. So what we get is V by 4. So if we apply our digital input at a combination of 0, 1, 0, the output voltage would be V by 4. So if you look into the it closely in the previous analysis, when the digital input was 1, 0, 0, 0, we got the output voltage as V by 2, and when it was 0, 1, 0, 0, we got the voltage as V by 4. And if we take the other combination, say 0, 0, 1, 0, we will get the output voltage as V by 8. And if we take 0, 0, 0, 1, we will get the output voltage as V by 16. So if we analyze them one by one, what we'll get is, we'll get the total summation when all of them are working together, where one will be V by 2 plus V by 4 plus V by 8 plus V by 6, and it is true if we use n number of total bits. So this expression extends up to V by 2 to the power n, where n is the total number of bits. So if the total number of bits is 4, then we will restrict the expression till this. Now if it is 5, then we will have another term which will be V by 32. Now this particular expression can be rearranged in this fashion, where V0, V1, V2, V3 and Vn minus 1 are similar voltages. Okay, if they are present, they are at high logic. If they are absent, they are 0. So we can better understand this using a simple numerical example. Let us try to understand a simple 5-bit ladder network with the digital inputs as 11010. So let the low logic voltage be 0, let the high logic voltage be 10. Now we'll have to calculate the output voltage of the D2A converter. So what can we do? We know this expression. Please look into this expression very carefully. We have a 5-bit ladder network, so 2 to the power n is replaced by 2 to the power 5. Now we will consider only the 5 terms. Now this 2 to the power 0 means the least significant bit, which corresponds to the 0 here. 2 to the power 1 means the next bit 1. 2 to the power 2 is 0. 2 to the power 3 and 2 to the power 4 both are high logic. So what we will do is, high logic here means all the voltages are present, and where the voltage is not present, it will be replaced with a 0. So if we substitute the values of voltage in this particular expression, we can see we are considering low logic as 0 volt and high logic as 10. So what we will do is we will replace the voltage in the in this particular expression. Now we know v0 v0 is the least significant bit voltage, which is 0, so it has been replaced with a 0. V1 is the next voltage at the input, which is 10, so it has been replaced by 10. Now V2 is again 0, it has been replaced by 0, and the V3 is again V3 is this, which is again high, it is replaced by 10, and similarly V4. Now the terms multiplied with 0 will get cancelled, they will not be there. So we will have three terms. We'll take the 10 as common, and inside will be left out where 2 to the power 1 is 2, 2 to the power 2 is not there, 2 to the power 3 is 8, and 2 to the power 4 is 16. So if we compute this, we will get an output 8.125 volts. So this is how we can actually calculate the output voltage for all possible combinations. Now this was extended to a 5-bit ladder network. This will remain the same whether you are discussing a 2-bit ladder network or a 3-bit ladder network or a 4-bit ladder network or a 5, 6 or in bit ladder network. So in this discussion, what we have seen is a brief outline about D2A converters, and we have seen the construction of a D2A converter based on R2R ladder network. We studied and analyzed a 4-bit D2A converter. Then we had a numerical example solved for a 5-bit D2A converter based on R2R ladder network. So thank you viewers for watching this video. I hope I will be able to provide other videos related to analog electronics and digital electronics in future. Stay tuned and watch my channel on a regular basis, and if you people want to get updates on new videos, then do try to subscribe the channel. Thank you very much for your support and your patient viewing. Thank you very much.